to FinFET, right? This is the reading you can read. But now, so FinFET is what? Why we call it FinFET? We should start calling it double gate. I think it's very natural for you. You already found out that fully depleted SOI is just like having two gates. Why don't I control them at the same time, right? Just like at the very beginning, we look at this graph. Hey, we just make V1 and G1, VG1 and VG2 in this direction. Then they go from both inversion to depletion to accumulation. A very strong control, right? So then we can do that, but now you realize that, hey, the oxide is too thick. I don't have enough power, right? So if the technology allow, why don't you have two gates, right? So indeed, if we try to look at the electron integrity, if you can try to do two gates, basically you effectively reduce the oxide the silicon thickness by half, because due to symmetry, you have two gate control effectively. You only have half the thickness. Remember, what's the goal of doing the scaling? We want to reduce the thickness of the depletion region, right? Maybe I should say we want to reduce the thickness of the depletion region, right? We want to reduce the oxide thickness, right, for scaling. So if I can add another gate on the bottom, then it will be good. And indeed, this is the scaling length we have discussed earlier, lambda, right? If I'm able to use double gates, I actually have a smaller scaling length, right? We want to have a smaller scaling length. That means I can scale my transistor smaller while avoiding the short channel effect, right? And this is like, if this is from the bulk picture, hey, instead of having this bulk not having control, I just add another part so that now I have a perfect control on my transistor. Right? Is this clear? Any questions about why we do double gate? Right, so our goal is to have the better control. Here, show you the scaling, right? Now, scaling. Now, how to read it? Here you're trying to say what is the silicon thickness width to gate length ratio. Okay, so it's like was TSI divided by LG, right? So this inside the region, right, the gray area means it is working, or say no short channel effect. Okay, if you have a single gate, for example, if I want to scale to 50 nanometer, right, for one gate, which is the bulk, right, it means I need TSI divided by LG equal to 0.2. So I need to make TSI pretty thin, 0.2. If I have 4 gates, for example, right, can have TSI divided by LG equal to 1. So basically, I'm allowed to do this. Okay, I don't want to draw 4 gates, right? Let me stop here. Let's say 2 gates. TSI divided by LG equals 0.5. So what does it mean? For this transistor, I need to make this really thin. If I have gate length like this, LG, then this is TSI. I need to make it so thin. If I have 2 gates, what does it mean? This is LG. I can make this thicker. Is that okay? So basically, for the same technology, I can relax it, Or from another point of view, if say I only have 0.2, let's say my goal is that I only have, I can do 0.2 TSI, right? Let's say if it is 0.2. Then for double gate, I can do to 25 nanometer. For single gate, you only can scale to 50 nanometer. So if you use single gate SOI, the smallest one you can do is 50 nanometer when TSI over LG is 0.2. But if I use double gate, I can scale it to 25 nanometer. And for 4 gates, then I can even scale to 10 nanometer. Is that clear? Any questions? So naturally, if you think 2 is good, you'll think I want 3, 4, 5, okay? So there are 2 types of gates. We can even do tri-gates. This is the silicon. This looks like what? This is a fin, right? Like the fin of a fish, right? The fish is here at the bottom, the body, and then you have this fin. This is the source and this is the drain. And what we're doing, you just wrap the fin by the gate. So how many gates do we have in this case? Can you tell me, can you count it? How many gates for the left one? How many gates?
4.
4. 1, 2, 3. Do you say that this is 4?
Yeah.
Okay, you are not wrong. No problem. But because this is fake, the industry will say that this is not the 4th gate because it is fake oxide. It has very small control. Okay. So here they will say you have 1, 2, and 3. So this is a tri-gate. Why I want to point that out, right? You're good. You say it's 4. Because now here, can you continue? How many gates do we have?
2.
2. 1, 2, right? This time, this is no longer because this is very fake. Fake what? Means what? C ox is small. So you basically has no control. Okay, so this is what usually people call FinFET. But there's no reason why we don't want to go to tri-gate, right? The reason at that time they do FinFET was because for the fabrication. In order to make this so narrow, they need to add a hard mask here, right? So actually, this was like they claim invented in UC Berkeley. I was in that group, but I came late, right? I came in 2001, so they already did that, right? But the reason is because they need the hard mask in order to make it small. At that time, they still don't have the ability, right, to print very small feature. So how do they do this? They need to use something called spacer technique. We're not going to cover, but because of that, then we have this. But later, if you try to find the trade-off, actually, this is pretty good also, right? There are many things you need to think about. But anyway, in the industry, you will hear about people say tri-gate, FinFET, and that's what they mean. But it's not, it won't hurt to confirm with people if you're discussing with your customer or your colleague, because they may hand-wavingly sometimes call this FinFET, sometimes call this tri-gate. It really doesn't matter. The most important thing is what really they are talking about. So confirm with them. Okay. So if you say tri-gate, wow, people becomes very creative. FinFET is double gate. Tri-gate is like what we just saw. Well, they say I can make it rounding. I have more control. They call this omega gate. And omega gates actually, it's just like omega, you have some overlap at the bottom to further increase the control. You might say, why don't you wrap over? It's just because difficult to make. Think about we are doing lithography and etching from there, okay? And eventually all around, and that's what we call nanowire. And that is the next generation, okay? And nowadays, there's one more thing, is called nanosheet. It's just like nanowire. Okay, but they make it a sheet knife because it's easier to fabricate. And the overall performance will be better than nanowire. Of course, you're right. In terms of control, nanowire is better than nanosheet, right? Nanosheet is, if you make it extreme, it's just like a double gate fin. So you find the middle that gives you the best results. Maybe you don't know what I'm drawing, right? This is silicon. This is the gate electrode. Let's say gate metal. Okay, and the inside is the oxide. Same here, silicon, oxide, and then metal. Okay. Any questions? And so yeah, this keyword, I hope that you can learn, memorize it good for your interview. This all called GAA, both of them, 1, 2, 1 and 2, right? Just for you to learn. It's called gate all around. Just wrap everything, have super good control, right? And people are very innovative. Wow, can I stack them? Yes, you can do whatever, but you need to make it and make it cheaply. That's the main point, okay? Now, how do you make the FinFET? This is just a very simple example, right? So again, you start with SOI wafer. Do you recognize that? Last time we already talked about SOI wafer, right? You can go back to take a look again, but assume we already have the wafer, means I have the SOI on top with the barium oxide, right? So what do? We etch it, you see? We etch it, then we become a fin. So this is completely isolated, right? We just etch it, assume you are able to do that. And this is called fin height and fin width. Then what do? We deposit the gate material, first the oxide and then the metal. We do some planarization to polish it first, because now it's a 3D transistor. Well, the reason we want to do planarization is to ensure the good lithography process. Lithography is a process for you to define pattern layer, right? If you have a topology, then you are going to have defocusing in different regions. You are not going to have a good resolution. That's why we do planarization. This process is not going to affect the structure of FinFET, right? It is more for the lithography, okay? Now, I also want to mention, I keep saying this is oxide, but now it is not silicon dioxide. We usually use hafnium dioxide, which has a dielectric constant in the range about 24. What is the dielectric constant of the silicon dioxide? Anyone remember?
3.9.
3.9. You know, that is like what? 6 times higher. Why do we discussed this already? Why do we want to use high K? This is called high K. Why do we want to use higher permittivity?
Higher capacitance.
Higher capacitance, very good. So for the same thickness, you have higher capacitance. Then why don't I just make the silicon very thin? C equal to epsilon over T. Yeah, good. You say that you can increase this one, then I have high capacitance. Well, I can also reduce T to make it higher. Why don't I just make it thinner? Why I want to spend money to develop a new material? What's the problem of making T very thin?
Band-to-band problem.
Tunneling.
Band-to-band tunneling.
But not band-to-band tunneling. Remember, the gate tunneling is an insulator, right? So you are going to have tunneling directly through the oxide.
Oh, okay.
Right? Yeah. Very good. Yeah? So you kind of link to here, although a little bit off. So it's direct tunneling. Okay. We cannot have a lot of gate leakage current. So that's why we need to keep the oxide thickness. We keep it thick. Then how do we get large capacitance? We use high K dielectric. Okay, is that okay? So let me let me just draw a cross section so you know what's going on here. A dash. So basically you have a fin. This is the fin. And then on here you have the high K, hafnium dioxide. And then outside you have the gate metal. Okay. That is what you get. Okay. Then we need to pattern the gates. You see what we have done, you just edge away the gates, and this is the gate length. Okay. And then we do source string extension implant. We try to make it N plus at both sides. After that, we will do something called epitaxial growth. Because this is very small and it has very large contact resistance, right? So we want to increase the area, right? This will increase the area so that the contact resistance will reduce to the source string, right? But this drawing is not good. In reality, it will be something like this, a diamond shape. Okay, when you grow, the whole source string will just blow up. This is the gate, right? This is the gate. This is the source, this is the drain. Of course, here we are not using SOI, so you actually have silicon underneath, but doesn't matter, it's still the same, right? Is it clear for this picture? Okay, so that is a FinFET. This is the gate, this is source, and the other side is drain. The current flow from here to here. This is the current. Okay, so it's a 3D, they call it 3D transistor. Now, there are two types of FinFET. One is bulk, one is SOI, right? What I just showed you is SOI. So what do you call? What do you do, right? Just like what we did, this is the box. This is the SOI, right? So after the etching, you have this fin on top of SOI. Okay, so this is SOI. Another way is we still have the bulk transistor, no SOI. We just etch it. After etch it, we just fill up with oxide for isolation. But this is bulk, so I can have body contact. Okay. Just two different types. Right. The good thing about bulk is what? Wow, lower wafer cost, cheaper, better heat transfer. I already mentioned to you now the heat can go through the silicon. It is not brought out of the box. You can also have body effect, right? But you need some so-called anti-punch through, just like channel doping, right? Usually you have the P-type doping to avoid the source and drain punch through, right? So here we are doing a cut here, right? So punch through is here. The current can go from here to here because you have bulk. In SOI, they are blocked. But how do we prevent it? We just make this very pre-pass, right? Then you have the PN junction to avoid them from punching through. Right? So this is a 3D. Is that clear? Any questions? Okay, so we know the structure, right? Now, here is the epitaxial growth I showed earlier, just a nicer picture. But you see that for PMOS, we are going to add silicon germanium as the source string. Why is that? Because germanium has a large lattice constant. I will cover more about this later. And because it's a large lattice constant, it's going to have some compressive stress. It goes to squeeze it to the channel. And why we want that? It can increase the mobility. I will discuss later. But anyway, the source string, they use silicon germanium. So they are bulky. Think about in the classroom, we have some bulky people come in. they're going to squeeze those at the middle. They feel compressive stress, mobility of hole will increase. In NMOS, opposite, we put carbon, right? Why? Because carbon has a smaller lattice constant. Then what will happen? Anyone? If I make a smaller lattice constant in the source string, what will happen to the channel? When I have a big thing at the source and drain, I compress the channel. When I have a small thing at the source and drain, what do I do to the channel? You try to push this away, right? You have a tensile stress. Okay, this increase the mobility of hole, and this will increase the mobility of electron. So you have a higher perform FinFET. Is that okay? Am I going too fast? I will stop here. But any questions, please let me know.